Hello and welcome. We'll be doing a chapter of book 2, 12th standard book 2, that is Halogen Derivatives. So today we are doing the first chapter of organic chemistry, that is Halogen Derivatives. Well, before starting with halogen derivatives, I would like to tell you that your organic chemistry here in 12th standard is divided into some functional groups. Like we will be studying about functional group 1, functional group 2, functional group 3. Halogen derivative is different from these three chapters because halogens we don't consider them as a functional group. Their name always comes in prefix of the word group, that's why they are not considered as function group. If I talk about function group 1, functional group 1 basically involves OH and OR group. So in functional group 1, we will be studying about the ethers and alcohols and phenols. If I talk about function group 2, it comprises of carbonyl compounds. They are considered as derivatives of carbon monoxide. So here in this case, in function group 2, we will be studying about aldehydes, ketones, carboxylic acids and their derivatives. If I talk about function group 3, they are basically nitrogen derivatives. So we will study about amines and diazonium salts. Not only amines and diazonium salts are there in function group 3, we have cyanides and isocyanides also, but they are not there in CBSE syllabus, so we'll stick to our studies of amines and diazonium only. So today I'm going to start with halogen derivatives, and I'll tell you what halogen derivatives are. Well, as you people are quite aware of, that here I have an alkane, very simple alkane, that is methane. If I remove a hydrogen and I add a halogen, I will get an alkyl halide. Suppose I have got a compound like this. This compound is methyl chloride or chloromethane. Chloromethane is IUPAC name and methyl chloride is a common name. So this is a halogen derivative. We call it alkyl halide. Likewise, if I have benzene and I remove one hydrogen and add a halogen to that, I will get a compound like this. This compound is chlorobenzene. Here in this case the common terminology is aryl halides. So if a halogen is attached to an alkyl group, we call it alkyl halide. If halogen is attached to a benzene ring, we call it aryl halide. Dear students, before starting with the chapter, I want to tell you one thing, that no matter whether we are studying about halogen derivatives or function group 1, 2, 3, anything. Suppose we are talking about alcohols or phenols or ethers. First what we have to do, we have to learn their structure, then their method of preparation, then their properties. And properties involves both properties, physical properties and chemical properties. So by now we know what is alkyl halide and what is aryl halide. Now the second step which comes is how to prepare them. So we'll study about their preparation. So we'll see the preparation of alkyl and aryl halide. First I am telling you preparation of alkyl halides. How to prepare alkyl halides? I can prepare it from alcohols. The preparation of alkyl halide can be done in different manners. One among them is the preparation from alcohols. How to prepare from alcohols? Again, in that I have got a method of reacting it with halogen acid. So from alcohol by reaction with halogen acid. If I talk about halogen acid, what are these halogen acids? You know very well, we have some common halogen acid like HCl, HBr, HI. So I am talking about these acids, HCl, HBr and HI. So from alcohol we are going to prepare an alkyl halide by reaction with halogen acid. In that, first is chlorination. I will replace the OH group with chlorine. So suppose I have got a compound that is CH3, CH2OH, and I am reacting it with HCl in the presence of a Lewis acid. That Lewis acid can be AlCl3 or it can be ZnCl2 or FeCl3. I can use any one among them. I will get a compound that is CH3, CH2, Cl plus plus H2. See what is happening. H positive from here is combining with OH negative and that is coming out as H2O. So OH is getting substituted by chloride. But I want to tell you one thing, that although you are putting catalyst, since this is a primary alcohols and primary alcohols are less reactive, so you have to heat in this case. Delta represents heating. So not only you have to put a Lewis acid like AlCl3, ZnCl2 or FeCl3, but along with that you have to heat. On heating, the H positive from acid will combine with OH negative, they will come out as H2O and you will get alkyl chloride. Now had it been a secondary alcohol, the situation would have been different. Suppose I have got a secondary alcohol like this. I am reacting it with HCl. Again in the presence of the same catalyst, I am taking an example of AlCl3. It can be AlCl3, ZnCl2, FeCl3, anything like that. Any of the Lewis acid. But since 2-degree alcohol is always more basic, it has a tendency of donating OH negative ion very easily. So it will combine with H positive, it will come out as H2O. I will get a compound that is CH3, CH, CH3, Cl plus H2. Likewise, if I talk about a 3-degree alcohol, CH3, 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 OH, and I am reacting it with HCl. Again in the presence of AlCl3, again H and OH, they will come out as H2O and I will get alkyl halide, that is CH3, 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 Cl plus H2O. So see, this is how you can prepare alkyl chloride. I am reacting alcohol. See, again a recap, how we are preparing alkyl halides from alcohols. How from alcohols? By reaction with halogen acid. In those halogen acids, the example I have taken is of HCl. So chlorination is what we are doing. If you react primary alcohol with HCl, you have any alcohol, no matter whether it is primary, secondary, tertiary, you have to add a catalyst, and the catalyst is a Lewis acid like AlCl3, ZnCl2 or FeCl3. This is a catalyst which you have to add. But since primary alcohols are least reactive, you have to heat in that case. You need not to heat in secondary and tertiary alcohols because themselves they are very highly basic. They have a tendency of donating OH negative ion easily. So my dear student, this is how you can prepare alkyl chloride from alcohols. Dear student, what we are doing? We are doing preparation of alkyl halide. But I want to tell you one thing, that the same reaction can be used as a property of alcohols. So I will tell you how the same reaction is helpful in functional group 1, in OH. This reaction is the preparation of alkyl chloride, but this is also the property of alcohols. Primary alcohols are least reactive, secondary alcohols are slightly more reactive, and tertiary alcohols are most reactive. See, I tell you, as far alcohols are concerned, alcohols, they are transparent. So if you have taken an alcohol in a test tube, you can see through it because it is transparent. But if I talk about alkyl chloride, they are translucent. They are turbid. So if you add HCl in 3-degree alcohol, if you add HCl in 3-degree alcohol, you will get immediate turbidity. because they are most reactive. They have a tendency of tolerating OH negative ion most easily. Likewise, if you add HCl in the presence of BlCl3 in secondary alcohol, you will get the turbidity after some time. So we can write turbidity after some time. Generally it takes around 5 minutes. But in case of primary alcohol, the turbidity is only on heating. If you are not heating, the reaction will not occur and you will not get turbidity. So what is happening? It is not only the preparation of alkyl chlorides from alcohols, it is also a test to differentiate between primary, secondary and tertiary alcohol. Primary alcohol on reaction with HCl in the presence of AlCl3 will give turbidity only on heating. Now suppose I have got a test tube and that test tube has got some alcohol. So that alcohol, as I told you, is transparent. If I add some HCl into that and some AlCl3 into that, immediately if I am getting turbidity, that means it is a 3 degree alcohol. If I am getting that turbidity, say after some time, 2, 3, 4, 5 minutes, that means it's a secondary alcohol. But if I am not at all getting turbidity and the turbidity is coming only on heating, that means it's a primary alcohol. So this is used as a test to differentiate between primary, secondary and tertiary alcohols by the name of Lucas test. So same reaction can be used at 2 different places. You can use it in the preparation of alkyl halides, chloride, and you can also use it in a test to differentiate between primary, secondary and tertiary alcohols. So this is what Lucas test is. And this is how we can prepare alkyl chloride from alcohols. Now chlorination we have done. Second we'll move on to bromination. We'll see how to do bromination. So second is bromination. But before starting with bromination, I would like to tell you one thing, that you will hardly find this acid in lab. You will not find this acid in lab because this is unstable. If you have got 2 moles of HBr, they will decompose into H2 and Br2. HCl as such is quite stable because chlorine is a smaller halogen. If we talk about the bond length between H and X, it is smaller in chlorine. Chlorine is smaller bond, so HX bond is smaller. Smaller bond means stronger bond. So it is difficult to break this bond and that's why it is quite stable. Now if I move on to bromine, bromine is slightly larger in size, so the bond will become longer. Longer bonds, they are always weaker. So HBr is unstable, it decomposes into H2 and Br2. That's why we hardly get HBr in lab. Whenever we need HBr, we have to prepare it and then we have to use it. So what we are going to do here is, suppose I have got alcohol that is CH3CH2OH. Instead of using HBr, I will use potassium bromide. And I will use a strong acid like concentrated H2SO4. I will get compound CH3CH2Br plus KHSO4 plus H2. And in this case, you have to heat it also. Now the question comes to our mind, why we are using potassium bromide? What is happening over here? See, in the first step, this potassium bromide is reacting with H2SO4 and will give you KHSO4 plus HBr. The desired HBr is here. And this HBr will react in the second step with alcohol, that is CH3CH2OH plus HBr will give you CH3CH2Br plus H2O. So this is how the reaction is proceeding. So we are over with bromination. Again a recap. What we are doing? We are preparing alkyl halides. How? From alcohols. How from alcohols? By reaction with halogen acids. In those halogen acids, we have already used HCl, so we have done chlorination. After chlorination, in chlorination also, what we did? Lucas test. After chlorination, we did bromination. In bromination, I told you that since HBr is unstable, you have to use KBr along with concentrated H2SO4. When KBr reacts with concentrated HBr, and that HBr immediately reacts with alcohol to give you alkyl bromide. Now the third one is iodination. We'll see how to do iodination. First was chlorination, second was bromination, and the third is iodination. Again, if HBr is unstable, HI is highly unstable. Because when you are moving from chlorine to bromine, from fluorine to chlorine, chlorine to bromine, bromine to iodine, as you are moving down the group, the atomic radii is increasing. As the atomic radii is increasing, the bond length is also increasing. As the bond length is increasing, the bond is becoming weaker. It becomes easier to break that bond. So if HCl was stable, HBr was slightly unstable, and HI is highly unstable. Because iodine, if I talk about iodine, it has got a larger atomic radii. So HX bond length is quite large, and that's why it's a weaker bond. Now we'll see how to carry out iodination if we do not have HI in lab. Again, you have to take CH3, CH2, OH, primary alpha alpha. I am reacting it with potassium iodide, like I use potassium bromide in this case. But this time I am not going to use H2SO4. Instead of that, I will use H3PO4. I will get compound CH3, CH2I plus KH2PO4 plus H2. Now students, the question which comes to our mind, why we are using H3PO4 instead of H2SO4? In bromination we used H2SO4, but in iodination I am using H3PO4. This is your NCERT question. This is in text question number 10.2. Same question is asked there. Why during iodination of an alcohol by Ki we use H3PO4 instead of H2SO4? I'll explain that to you. Again, I'll tell you how the reaction is occurring. Actually, in the first step, it is potassium iodide that is reacting with H3PO4. It will give you KH2PO4 plus HI. And in the second step, the HI found in the first step will combine, that will give you alkyl iodide along with water. The question comes to our mind, what would have happened if in case I would have used H2SO4 instead of H3PO4? Well, in that case also, in the first step, it is Ki that would have reacted with H2SO4 to give you KHSO4 plus HI. And what we are expecting that this HI should have reacted with alcohol like it is doing here. But the situation is different now. H2SO4 is not only donating proton, it is not only giving H positive ion to form HI, but H2SO4 is a good oxidizing agent also. That would have got converted to H2SO3 along with an oxygen. And this oxygen would have combined with 2 moles of HI to form H2O plus I2. That means had it been H2SO4, initially it would have formed HI, but then it would have decomposed this HI to I2. Because H2SO4 as such is a good oxidizing agent. And since all HI would have undergone decomposition to I2, there would have been no HI to react in the second step. So alkyl iodide would not have formed. That's why instead of H2SO4 we use H3PO4. H3PO4 will simply donate a proton to form HI like it is doing here. And since it is not a good oxidizing agent, it would not decompose this HI to I2. So this is the answer of your in-text question number 10.2. H2SO4 is a good oxidizing agent. It will decompose any HI formed to I2, thus preventing iodination of alcohol. So by now what we have done chlorination, that is Lucas test. Bromination, KBr plus H2SO4. Iodination, Ki plus H3PO4. And in-text question number 10.2. See, by now a question would have been coming into your mind, why we are not using HF? Why it is chlorination, bromination, iodination, not fluorination? Dear student, in that case I would like to tell you that HF, if I talk about HF, has got a prominent intermolecular hydrogen bonding, and that's why it does not donate any H positive ion. Since it does not donate H positive ion in the free state, it does not act as a halogen acid, and that's why we cannot carry out fluorination by this method. We can only carry out chlorination, bromination and iodination. So this is how we can prepare alkyl halide from alcohols by reaction with halogen acid. So halogen by reaction with halogen acid is over. We'll move on to the second part, that is by reaction with phosphorus halide. Phosphorus halide, we have two phosphorus halide like PCl3 and PCl5. PX3 and PX5, phosphorus trichloride and pentachloride. So if I got a compound like CH3, CH2OH and I am reacting it with PCl5 in the presence of an organic base, that is pyridine, that is C5H5N. This is an organic base, pyridine. I will get a compound that is CH3, CH2Cl along with POCl3 and HCl. See, you have got 5 chloride ion. One of the chloride ion will combine with H, that will come out as HCl. The another chloride ion will substitute this oxygen, so it will come here, you will get Cl. You are left with PCl3 and oxygen, so they will come out as phosphorus oxychloride, POCl3. Here I would like to tell you one thing, dear students, why I am using pyridine, that is organic base, it is basic. We use a base whenever the byproduct is an acid, and if the byproduct is a base, we use an acid as a catalyst. So here in this case, since one of the byproduct is an acid, I am using an organic base as a catalyst. It will extract out this HCl. Now what will happen if I take PCl3? In that case, I have to take 3 moles of CH3, CH2OH. Again in the presence of pyridine. 3 OH will get substituted by 3 chloride ions. I will get 3 moles of CH3, CH2Cl plus POH thrice. These 3 OH they will come here, these 3 Cl they will come here. They will substitute each other. Now the question comes to your mind, why we are using pyridine? As I told you, pyridine is an organic base. That means the byproduct is an acid. So this is an acid. This is what? This is H3PO3, phosphorus acid. So since byproduct is an acid, we are using pyridine or a base as a catalyst. After this is how we have prepared an alkyl halide from phosphorus halides, that is phosphorus trihalide and phosphorus pentahalide. Next is by reaction with thionyl chloride. Thionyl chloride is SOCl2. So what will happen if I react an alcohol with SOCl2? If I got a compound CH3, CH2, OH, and I am reacting it with SOCl2, again I am using C5H5N, that is pyridine as a base. If I am using pyridine as a base, by now you know, if a base is used as a catalyst, that means the byproduct is an acid. So in this case, I will get CH3, CH2, Cl plus SO2 plus HCl. Now since SO2 is a gas, that will move out. HCl is a gas, that again will move out. You will get your alkyl halide in pure state. And that is a advantage of this method, that the alkyl halide you will get will be in the pure state, because both the byproducts, that is SO2 and HCl, they are in the gaseous state. They will move out of the system, leaving behind pure alkyl halide. So this is how you will get pure alkyl halide. My dear student, as we will proceed in this chapter, as I will tell you, once I tell you the chemical properties of alkyl halide, in that I will teach you nucleophilic substitution, SN1, SN2 reaction. This again is an example of a nucleophilic substitution reaction. This comes under a topic of SNI, that is nucleophilic substitution internal. Here the nucleophile, one part of the compound acts as a nucleophile, and that attacks on carbocation. So this is SNI, nucleophilic substitution internal, and you will get your alkyl halide in the pure state. That is the main advantage of using this method. So this is all about method of preparation of alkyl halide from alcohols. In that what we did, by reaction with halogen acid, by reaction with phosphorus halide, trihalide and pentahalide, by reaction with thionyl chloride. Now what are rest of the methods by which we can prepare alkyl halide? It's not only alcohol from which I will get alkyl halide. There are plenty of other methods also. I tell you, the second method which I am going to use here is from alkane. Second is from alkanes. How from alkanes? We have already done in 11th standard, that is by free radical substitution. By free radical substitution. Although I will tell you that the example which I am going to tell you is from the 11th standard, but definitely I am going to enrich your knowledge as far as free radical substitution is concerned. Because although this reaction is in the 12th standard, but it is a bit more sophisticated over here. Your knowledge has to be enriched. Then only you will be able to do some of the questions. I am going to tell you that question also. So suppose I have methane and I react this methane with Cl2. In the presence of sunlight, I will get CH3Cl along with HCl. Just a recap how this reaction occurred. In 11th standard we did that it is Cl2 in the presence of sunlight, homolysis will occur. One of the electron will come to one chlorine, another electron will come here. You will get 2 moles of chlorine with unpaired electron, that is free radical. In second step, you have CH4, I can write it like this. I have one of the free radical from here will attack on this hydrogen. So one of the electron is coming on hydrogen, another one is on carbon. H free radical and Cl free radical, they will come out as HCl. And you are left with CH3 free radical. This CH3 free radical will then attack on a chlorine molecule, that will give you CH3Cl along with Cl free radical. It is carrying out homolysis. So one of the electrons is coming here, another one is coming here. So you will get CH3Cl along with Cl free radical. This is how this free radical substitution is occurring. In this, I would like to add one more thing. This is from alkane. See, I would have taken that reaction separately, but since I had to teach you a concept, I am taking it here only. I will tell you, along with this, I am telling you preparation from alkenes also. Now suppose I have got an alkene, that is CH2 double bond CH2, and I am reacting it with Br, but not in the presence of sunlight. I am not taking sunlight. In dark. In dark, what will happen? Addition will occur. We have done this in 11th standard. So what I will get is CH2Br, CH2Br. I am carrying out this reaction in dark, and the reagent over here, the solvent is carbon tetrachloride. Dear student, again a recap before moving further. Again a recap. How we can prepare it from alkane? Alcohol I have already told you. From alkane. How from alkane? Free radical substitution. If you react an alkane with a halogen in the presence of sunlight, free radicals will be generated. You will get free radical compound, you will get alkyl halide. So this is what you are getting. CH3Cl, free radical. I have told you this mechanism also. Same, in case you have got alkene, you are reacting alkene with a halogen, but the reagent is CCl4, that is simply a solvent, and in dark, not in the presence of sunlight. What you will get? You will get additional product. They are getting added to the double bond. No substitution, it is addition. So in the presence of sunlight, it's substitution, but in dark, it is addition. Here I would like to add two things. The first thing is that bromine in CCl4 is orange color. Once this bromine will undergo addition reaction, the orange color will decolorize. Alkenes and alkynes undergoes addition reaction with bromine. They add bromine, but alkanes they does not. So alkenes and alkynes, when they add bromine, they decolorize the orange color of bromine in CCl4, but alkanes they does not. Hence this reaction is used as a test to differentiate between saturated and unsaturated. All saturated hydrocarbon will not decolorize the orange color of bromine in CCl4, whereas saturated will not decolorize, unsaturated will decolorize. They will decolorize the orange color of bromine in CCl4. So this is how the reaction is happening. This is the first concept related to it. The second concept is addition of bromine to a double bond is always an anti-addition. Anti means the two bromines, they will not get added from the same side. If you can see here, one bromine, if it is projecting downward, the another one is projecting upward. They are not getting added to the same side. So it is an anti-addition. Bromination of an alkene is an anti-addition. Both the bromine, they are in the opposite direction. Why it is so? Well, if we talk about double bond, there is a homolysis in double bond. So you will have these two free radicals. Now these two free radicals, pi bond has got, see this is sigma bond and this is the pi bond which has got broken. You have got two free radicals. These two free radicals will experience repulsion. So the single bond will tilt. They will move opposite to each other. And to these two free radicals, then bromine will get added. So this addition is an anti-addition. So by now we have seen free radical substitution and we have seen free radical addition. This is how we can prepare alkyl halide. Again, in this, I will enrich your concept as far as this is concerned. I am giving you one example. Suppose I have got a compound CH3 CH double bond CH2. I am reacting this with Br2 in the presence of sunlight. Dear students, when I am writing Br2 in the presence of sunlight, that basically means substitution is going to occur. As I told you, in the presence of sunlight it is always substitution, but in dark it is always addition. So if I am writing Br2 in the presence of sunlight, substitution is going to occur. But substitution cannot occur on the double bond. Double bond always undergoes addition reaction. If I am saying substitution, that means this methyl is going to react. So one of the H will combine with Br, that will come out as HBr. Another Br will combine with this, you will get Br, CH2, CH double bond, CH2. You are getting allyl bromide. This is what you are getting. If you react same compound with Br2 but in dark, I told you earlier that in dark it is addition that occurs. So in this case you will get CH3 CH Br CH2 Br. This is what you will get. So in dark it is addition, but in the presence of sunlight it is substitution. Now let us move a step ahead. In free radical substitution, this example you have seen that in the presence of sunlight, Br will come here, one of the HF will move out, Br will come here, we will get allyl bromide. What about if I get a compound like this? If I reacted with Br2 in the presence of sunlight, see you have got two sides. No doubt in the presence of sunlight it is substitution that will occur. Substitution can occur here, substitution can occur here. But here you will get 1 degree free radical, here you will get 2 degree free radical. And since 2 degree free radical is more stable, so it will form quite easily. So this is the side where Br is going to attack. That means the major product will be like this. And what about this one? This will be a minor. This is a major product. CH2Br, single bond CH2, CH double bond CH2. This is minor product. This is minor product. Why this one is a major product? Because 2 degree free radical is more stable, and more stable free radicals they are quite easily formed. So this will react. So this is what you get. Now a question comes to our mind. Suppose I have got more than 2 degree free radical, what will happen? I have got this compound. Here this one is of 1 degree, this one is 2 degree, and this again is 2 degree. Now based on these 2 degrees, the two different products which are possible, are CH3, CHBr, CH2, CH double bond CH2. Or a second compound can be CH3, CH, 2CH, Br, CH double bond, CH2. See, both of them they are 2 degree. The question comes to our mind, if both of them they are 2 degree, then which one is more reactive? Where the Br will go? Which one will be the major product? Here in this case, this will be the major product. And this is the minor product. Again question comes to our mind, why? When both of them they are 2 degree, their stability has to be same. But no. As far this part is concerned, this is allylic free radical. This will form allylic free radical. That is a free radical adjacent to a double bond. Whenever a free radical is adjacent to a double bond, it always undergoes resonance. So that is always more stable. No doubt, both of them they are 2 degree. This is 2 degree, this again is 2 degree. But this 2 degree is adjacent to a double bond. That's why it will undergo resonance, and that's why it is quite stable, and that's why this is the free radical that will be formed predominantly. And that's why Br will attack here. So we'll see how it happens. Suppose I have a free radical . This is the compound I got, or I take one compound. I am writing it like this. I am taking the same compound. If I remove H from here and I form a free radical, what will happen? This double bond will undergo homolysis. You will get a free radical here, another free radical here. And this free radical will undergo resonance. You will get another resonating structure, that is CH, double bond CH, single bond CH2, free radical. This will again undergo resonance, that is CH2 free radical, CH, double bond CH2. So both of them they are same. So double bond is moving. That means the allylic free radical undergoes, that means the allylic free radical will undergo, this is the allylic free radical, this is from the double bond. So allylic free radical is undergoing resonance. Now whenever allylic free radical is attached to a double bond, it will undergo resonance. And whenever it undergoes resonance, it becomes more stable. So in this case, although both of them they are 2 degree, but this 2 degree will undergo resonance. And since it will undergo resonance, it will become more stable. And since it will become more stable, so it is the one which will be formed in major quantity. And that's why this will be the major product. Dear students, by now what I have told you how to prepare an alkyl halide from alkane. That is by free radical substitution. And alkene we have already seen, that is by addition. The substitution occurs in the presence of sunlight, whereas the addition occurs in dark. If we talk about substitution, it is a free radical substitution. And if we talk about the free radical, we have to see the stability of the free radical also. I taught you one thing, that whenever a free radical is adjacent to a double bond, we call it allylic free radical. It always becomes more stable due to resonance. And that's why that is the major product. Allyl halide will be the major product. Now the question comes to our mind, okay, we have learned this concept, where we are going to use it. For that again I will give you one example. This is your NCERT question, that is in text, question number 10.5, and last part, that is the sixth part. In that they have given you a compound like this, and they have said that we are reacting it with Br2. They have written UV radiation. UV means again that sunlight. What product will you get? Remember one thing, that since you have got UV radiation, since you have got a radiation, that means no addition. It is always substitution. The addition occurs in dark, but substitution occurs in the presence of sunlight or in the presence of a radiation. So in this case, we will have substituted product. See, addition product will be found on these two carbons, but as far as substituted product are concerned, here, and here you can get substituted product. Because these are the carbons which does not have a double bond. These are the carbons which have 2 hydrogen. These are the carbons from which hydrogen will get substituted by a halogen. The hydrogen is going to move out and the halogen is going to go there. Now the question comes to our mind, which among these hydrogens is more reactive? I taught you here, allyl free radical is more stable. So either this position or this position is more stable. So either the halogen is going to get added here or here. That means your answer will be here only. Because once you remove hydrogen, see, I draw this structure so that it becomes easier for you. You have one hydrogen, here you have 2 hydrogens, here again you have 2 hydrogens, here again you have 2 hydrogens, and here also you have 2 hydrogens. If you remove hydrogen either from this side or from this side, if I remove the hydrogen, H free radical I have taken out, I am getting a free radical here. And this free radical will undergo a resonance here. So likewise it will keep on undergoing resonance. So either the Br will get added here or here. That automatically means what? Br is getting attached to a carbon adjacent to that double bond. So this is the product you are getting. And this question is based on this concept. Stability of allylic free radical. Allylic free radical is always more stable. Say 2 degree free radical, they are more stable than 1 degree. 3 degree free radical, they are more stable than 2 degree. And if we talk about allylic free radical, they are more stable because of resonance. So this is what is happening here. So this is what is preparation of alkyl halide. From alcohol we have done, then from alkanes we have done, then from alkenes we have done. In alkenes, we'll move a step ahead. From alkenes, addition of X2. This is what we have already done. Addition of X2, that is an anti-addition. Now I tell you, by addition of halogen acid. By addition of halogen acid. So suppose I have got a compound like CH2 double bond CH2 and I am reacting it with HCl. It will undergo addition. I will get compound CH3 CH2 Cl. We have already done this in 11th standard. See what is happening, electromagnetic effect is taking place. This is a polar compound, H positive and Cl negative. So in alkenes, the pi electron will come toward one of the carbon, that will become negative, the another one will become positive. H positive will attack on the anion leading to the formation of CH3 and Cl negative will attack on the carbocation leading to the formation of alkyl halide. Now what will happen if as far this addition is concerned, you know very well that this addition is what? Markovnikov's. This Markovnikov's addition will get clearer from another example. Suppose I have got CH3, CH double bond, CH2. If I add HBr to this, again the pi electron will come here, this will become negative, this will acquire a positive charge, H positive and Br negative. H positive will attack on this anion, Br negative will attack on carbocation, leading to the formation of CH3, CHBr, CH3. See, the question comes to our mind, why electrons they are going here? Why this carbon is becoming negative and this is acquiring a positive charge? Because we know that 2-degree carbocation is always more stable than 1 degree. Had this carbon been a positive, this carbon would have acquired positive charge, it would have become primary carbocation, and primary carbocation are less stable. So reaction occurs to gain stability. Since 2-degree carbocation is more stable, this is the carbocation that will be formed. So this is how the reaction occurs, and this is very accurately Markovnikov's addition. But had the reaction would have occurred in the presence of a peroxide, I would have got different product, that is CH3, CH2, CH2, Br. Because in the presence of peroxide, it is free radical addition. In the presence of peroxide, homolysis would have occurred. That is, in case I would have got compound, the same compound I am taking, CH3, CH double bond, CH2. One of the electron would have come here, of pi bond, another would have come here. We know that 2-degree free radical is more stable and 1 degree is less stable. Less stable means more reactive. In that case, the Br free radical would have easily attacked on this free radical, leading to the formation of primary alkyl halide. So, if you are not using any peroxide, it is always ionic reaction, and in that case, it is Markovnikov addition. But if you are using a peroxide, then it's a free radical addition, then anti-Markovnikov or Karash effect or peroxide effect will occur. So this is anti-Markovnikov addition. And this is all about preparation of alkyl halide from alkenes. So by now we have seen preparation from alcohols, from alkanes, from alkenes. In alkenes we have done addition of halogen and addition of halogen acid. Here I will move again to alkanes. We'll just focus on alkanes, alkyl halide, bromide, iodide, which among them will be easily formed and why? Why not fluorides? So again we'll move on to the same reaction. So this is what happens in Markovnikov and anti-Markovnikovs. Second, I taught you from alkanes. And in that I told you that CH4 plus Cl2 in the presence of sunlight will give you CH3Cl plus HCl. Dear student, I want to tell you one thing, that by this method it is very easy to prepare alkyl fluoride. It is slightly difficult to prepare alkyl bromide. It is very difficult to prepare alkyl iodide and also difficult to prepare alkyl chloride. So by this free radical substitution we generally prepare chloride and bromide. The question comes to our mind, why not fluoride and iodide? Well, let's see how it happens. I have already told you the mechanism of this reaction. In one of the steps of that mechanism, what happens? It is CH3 free radical that combines with X free radical to form CH3X. If I talk about Cl free radical, that is smaller in size. So there is a prominent attraction between methyl free radical and halogen free radical. High force of attraction means more amount of energy will be given out. So chlorination is exothermic, and since it is exothermic, it is spontaneous. It occurs easily. If I move from chlorine free radical to bromine, the bromine free radical is slightly larger. Larger means the attraction between CH3 free radical and bromine is not prominent. Weaker attraction. Weaker attraction means the reaction is very slightly exothermic. So this reaction is very slightly spontaneous. But if I talk about iodine free radical, that again is very large in size. If I talk about iodine, very large. The iodine free radical is so large that it does not go very close to methyl free radical. Since it does not move very close to methyl free radical, the attraction is very less. That means the energy is not given out. In fact, this step is endothermic. You have to apply energy. So since it is endothermic, it shows some non-spontaneity. You have to apply energy, you have to bring it closer to methyl free radical, then only you will get methyl iodide. Now what about fluorine? If I talk about fluorine free radical, it is quite smaller, very small. It will come very close to methyl free radical. That means very large amount of energy will be given out. That means explosive reaction. So fluorination is highly explosive. Iodination is highly endothermic. So we do not carry out iodination by this method since it is highly endothermic. We do not carry out fluorination by this method since it is highly exothermic. So how to prepare fluoride and iodide? This is what I am about to tell you. By this method, you can get chloride and bromide. But if you want to prepare fluoride and iodide, alkyl fluoride and alkyl iodide, how you will get alkyl fluoride and alkyl iodide? That is what I am about to tell you. For that, we will carry out halide exchange. Halide exchange. What does that mean? That means that you will prepare alkyl chloride or alkyl bromide by this method. After that, you will change this halogen. You will substitute this chloride by either fluoride or iodide or bromide by fluoride or iodide. So that is halide exchange. In halide exchange, I am telling you first exchange by fluoride ion. For that, we can use Ag2F2 or AgF. Now suppose I got CH3, CH2, Cl by this method. I will take 2 moles of that and I will react it with Ag2Cl2 in the presence of CCl4. CCl4 is a solvent and I heat it. Ag2F2 I am taking. So these fluorine, they will substitute chlorine. I will get 2 moles of CH3, CH2, F along with Ag2Cl2. Halogen has got exchanged. Chloride ion has got exchanged by fluoride ion. This reaction is Schwarz reaction. So this is what Schwarz reaction is. Likewise, if I have to carry out iodination, so we have exchange by iodide ion. I have got CH3, CH2, Cl. I am reacting it with sodium iodide. The solvent I am using is acetone. Again I am heating it. I will get compound CH3, CH2I along with NaCl. The exchange has occurred. Chloride has got substituted by iodide. This reaction is Finkelstein reaction. So this is Finkelstein reaction. Dear students, in this session what we have done, we have learned what are halogen derivatives, alkyl halide and aryl halide, preparation of alkyl halide from alcohols by reaction with halogen acid. In that we did chlorination, in that we did Lucas test, then bromination by HBr, then iodination by HI. After that, we did preparation from alcohol by reaction with phosphorus halide, that is PCl3 and PCl5, by reaction of alcohols with thionyl chloride, and that was all about preparation from alcohol. After that, I switched over to preparation from alkanes by substitution, from alkenes by addition, anti-addition of halogens. I told you what's the difference in substitution and addition. Substitution will occur in the presence of sunlight, addition will occur in dark. In substitution, I taught you which free radical is more stable. 2 degrees more stable than 1 degree, 3 degrees more stable than 2 degree, and allylic is more stable because it undergoes resonance. After that, we talked about in free radical substitution that chlorination and bromination can occur easily. But as far chlorination and iodination is concerned, we had to carry out it in a different way by halide exchange. And in halide exchange, I taught you Schwarz reaction and Finkelstein reaction. So this is all about method of preparation of alkyl halides. In next class, I will teach you the method of preparation of aryl halides along with the properties, their physical properties, and we'll learn stereochemistry also, stereoisomers. So that is what I am going to teach you in the next session, and this is all for this session. Thanks a lot. Thanks for joining.